And how do you convert? Now, if you want to convert a Las Vegas algorithm into Monte Carlo algorithm, how do you do this? We had done this last time. Do you remember? And I had asked you to read probability. Let me write. There is an algorithm which takes expected cost E, okay, and has no error. This is what we have corrected. E is 8 by 3 to the power d. This is some algorithm A. I can always convert into an algorithm A whose worst case cost is equal to 10 times E. And this is a simple trick. This does not depend on recursive majority, anything. This depends on your understanding of probability. You have an algorithm which runs in this much time, okay, with no error. I just make it run slightly more time. Error is less than 1 by 10. So I have converted Las Vegas algorithm into Monte Carlo algorithm with almost the same cost. Okay, so the cost will be this, which is much less than 3 to the power t in our case. But how do you do it generally? What kind of theorem would you use here? Did you read concentration inequalities? Do you know what Markov inequality is? Okay, so can you do something with Markov's inequality? I want to change expected cost into worst case cost. Expected cost is over R. What is Markov's inequality statement? Right. So now, what is the probability that my algorithm will run more than 10 E times? Less than? Right. My expected cost is E, correct? So what is the probability that my algorithm will run more than 10 E times? What is it? Less than 1 by 10. This is simple algorithm, Markov's inequality. People know Markov's inequality or no? Should I write it down on the board? How many people? Huh? Preferably? Okay. And it is important that X is a positive random variable. And
what's the first thing you written before the bracket?
Probability, PR. The probability that I am going much higher than expectation is going to be very small. This is when I have a positive random variable, right? So then what I know is that my algorithm will barely run, hardly ever run for more than 10 times the cost. So what should I do? I'm allowed error. If it is running more than 10 E times, what will I do? Stop it and answer what? Answer whatever you like. I don't care. What is the probability that I am running for more than 10 E times? It's 1 by 10. Whatever I answer there, the probability of error is going to be at most 1 by 10. So how do I care? This is the simple. So again, these ideas are not difficult. I'm just reiterating them so that you understand the definitions. What is a Las Vegas algorithm? Its expected cost is something. There is no error. Again, error, expectation, all are with respect to R, not with respect to X. Correct? So expected cost is this, E, there is no error. So now think about, okay, let me make it pictorial. I think pictorially things make more sense. Okay. You have this bucket. You have these different balls, right? If you pick some ball, my algorithm will run E by 2 times. If you pick some ball, my algorithm will run 2E times. Correct? Notice these balls do not depend on the input. I'm not talking about this ball is not same as input. This is the random string R. So I pick a random string R, it tells me how much time I am running for. What do I know? The expected value of this is some E. Let me just make it so that the expected time I take, right? Correct. Now, what do I want to do? I want to create an algorithm where whatever ball I pick, I do not run more than 10E times. Correct? This is a problem because I know that some balls here might take E by 2 times or E by 10 times, but some ball here might take 100E times. Though, since the expected value is E, what do I know? If I look at the fraction of balls where I'm running more than 10E times is very, very small. This is Markov's inequality. This is Markov's inequality is exactly saying that the number of balls, so these are the balls where okay. So now if my algorithm runs up till 10E times, on all these balls it will correctly answer. It's a Las Vegas algorithm. On these, I don't care. Because this probability, this circle is very, very small. So on this, whatever you answer, it doesn't matter. It agrees with my input, it does not agree with my input, I do not care. These are small number of balls. Whatever be their answer, it doesn't matter to me. Because I'm allowed to make an error with probability 1 by 10. Yes. Yeah.
For 10 E cost.
Oh yeah, I do not care about constants. Like 8 by 3D, what C you are putting, so that it becomes, like you are saying that the C you can improve, right?
For the 1 by 10 case, we can just look at what that answer 0 by 1. So 50 times we are right.
Again, that's what I'm saying. I'm trying to emphasize that you are right. I'm not denying that. You can make your probability become 1 by 20, error probability 1 by 20, but those constants are immaterial. So I'm keeping things simple. I say my answers are 0 and 1. If it runs more than 10 times, I say I am wrong. Even then I am fine. Yes.
In that case, we have, like, if we say that we flip a coin and then answer, so in that case, won't it become like two-sided error instead of one-sided error? It will be harder.
This is two-sided error. All this is two-sided error.
So, but if we always answer just one, if it takes more than 10, then it becomes a one-sided error, right? Because we always get it right when it's 0. Like if it's less than 10, we always get it right, and if it's more than 10, if we always answer 1, we'll always get it right at 1 and wrong at 0.
There is no advantage of making this one-sided error. We're talking about error probability to be 1 by 10 or something. You can. You can. But what I'm saying, it doesn't matter. If you want to make it one-sided error, you can. But all of those one-sided, two-sided, error probability 2 by 3, success probability 3 by 4, success probability 0.9999, all of them will take constant times 8 by 3 to the power d many queries. This is what I am trying to emphasize. So I know we are getting stuck into these. You are right. You can make it one-sided. You can make the error probability 0.99, 0.999999, 3 by 4, 2 by 3, but I do not care. What I am saying is, with whatever error probability you want, you tell me the error probability in the beginning, constant, that error probability, one-sided or bounded error, whichever one you want, I can do it with C times 8 by 3 to the power d many queries, which are better than 3 to the power d many queries. So I indeed get an asymptotic advantage. Is order notation okay with all of you? Right? So we know that which one is correct? Again, I want, raise your hands. Is first one correct? How many people think first one is correct? Raise your hand if you think first one is correct. Raise your hands if second one is correct. People who have not answered, is order notation an issue? If it is an issue, you have to read about it. If you are doing a course on quantum advantage, if you are doing a course where quantum is better than classical, quantum is better than randomized in computation, we will show it for asymptotic advantage. So this O theta omega should be very, very clear to you. If it is not, read it. It's a must. There is no way I can show you advantage if you don't know what advantage means in computational setting. Okay, so clearly this is true, this is wrong. Okay, and intuitively what it says is that as d becomes larger, this is way, way, way bigger than this quantity. Okay, what I mean by that is you put your favorite constant, this will be less than 3 to the power d for some big D. Okay, this is how you compare algorithms. Yes?
First one is correct. Then like 3 to the d is also order of 3 to the d. Then we say that both of them are the same order?
No, because if both of them, that would have been a theta. That is called a theta when both of them are of the same order. If this and this both were true.
Not this and this. So like 3D is order of 3D. So like it's 1
Yes.
into 3D.
Yes, yes.
That would mean that 8 by 3 to the d is the same or is equal to order of 3D is equal to the 3 by 3.
But again, when I say this, what I'm saying is this is incorrect.
With the condition that the other is incorrect only we can say.
Yes. And actually, since you are getting into technicality, the correct statement, if you want to say the advantage, it would be that but then I wasn't even sure whether you know big O, theta, omega. I don't want to small o and complicate things more. Okay? But yeah, the point is, you have to understand computationally, as a computer scientist, what do I mean when I say 8 by 3 to the power d grows much smaller than 3 to the power d. So if you have an algorithm which runs in this much time, and you have an algorithm which runs in this much time, clearly this is better. Like we said, a root n times algorithm is better than n times algorithm. And n to the power 1 by 4 algorithm is better than n to the power half algorithm. Correct? So how many people are not okay with O notation? Read about it. Please read about it, okay? If you have problem, ask me, I will give you resources. Sounds good? But this has to be done. This you should understand. This is what we do in first course in programming, first year programming, and then definitely second year they learn. So I will assume this. There is no advantage which I can show without this. So please, okay? So then once you know this, now there is an algorithm which runs in C times 8 by 3 to the power D, which only makes an error in 1 by 10 and computes recursive majority. Okay? So now, what is the conclusion? After this, any deterministic algorithm takes 3 by D to the power D queries, but there exist, for all deterministic, there exists a randomized algorithm which takes only 10 by okay. So for recursive majority, randomized algorithm is better than deterministic algorithm. And we'll be doing same things for quantum versus randomized, the same order notations. That's why you have to understand order notation. Okay? So this we were able to show. For all deterministic, we created first a randomized algorithm whose expected cost was 8 by 3 to the power D. And there was no error. Correct? This was the first step. And from here to here, this is a what we call black box, where I don't need to look inside the algorithm. I don't care what was happening in the algorithm. I have any Las Vegas style algorithm, I can convert it into Monte Carlo algorithm. Okay? If you are not comfortable with whatever I did today, see where you had issue. Was it this step? Was it conversion from this step? Was it in both? I would be happy to answer these after the class. Okay, but remember, this is what we did. This is how we did it. First, we created a Las Vegas algorithm whose expected cost was this, but there was no error. Then we converted into Monte Carlo algorithm. Okay, great. So now you have seen algorithms where randomized does better. I can ask, what about randomized versus quantum? What do you think? Can quantum outperform randomized computation? Yes, no. How many people think quantum can outperform randomized computation?
On this problem or?
On some problem.
It might, but maybe not by a large factor.
If that was the case, we would not be studying quantum computing.
But in one of the previous examples you mentioned, I think the coin flipping one, where we have to check if it is balanced or unbalanced. For example, that one.
So no. So the question is, does there exist functions? Does there exist problems where quantum can give you large advantage over randomized computation?
There must be.
Exactly. So that's the point I'm saying. So again, yes, this is very, very clear. There are problems for which quantum does not give you any advantage over randomized, right? Like Deutsch-Jotza. But there are problems where randomized gives less performance than quantum, and that's the reason why we are studying quantum. Otherwise, we would just be happy with randomized. Why would we make a quantum computer if we can make our computation just with coin toss? Coin toss is so much easier to make. Why would you take care of electrons and photons and everything, right? So clearly, there are algorithms where quantum does better than randomized. Can you give me an example? Okay, sure. How does it work? So let me tell you, you know an algorithm where, randomized does better than quantum. Sorry, quantum does better than randomized. Sorry? You have seen an algorithm where quantum does better than randomized. Remember this? Seems familiar? Suppose I have a function which is of this form. You have an oracle given where for any x you can compute f of x. You remember how we computed it? X, b XOR f of x. You create an oracle for some f. The problem is find a. You can do quantumly in one query. Randomized, I haven't done the lower bound proof, but it can be shown that for finding every bit, you need at least one query. So you need at least log n many queries to find a. Okay, so this is the reason this came in the midst. Now I don't have to cover it. Now, I'm giving you the answer.
Could we get sample answer sheet?
No.
To see where we went wrong?
Whatever you want to ask me. I'm giving you what I think were more difficult questions. I'm giving you the answer to those. Otherwise, for others, if you have doubt, I will give you hints. You try to finish it then. If you can't, ask me, I will finish them. Okay? So this is called Bernstein-Masrani algorithm, and this was obviously question 3.
This was mentioned in extra reading, right?
Yes.
Okay.
Still, not many people did it. But this part was not covered in the class till now. Okay? So, and even in the extra reading, there are no calculations done. So it's not like if you had read that part, you would have been able to solve it in the exam. Okay? So, what happens here? This is my fx. Correct? I'm applying this circuit. What can I say? Again, these are k, some k minus 1 or k qubits, right? I will not... right? I can ignore this h. This becomes the phase oracle. There is h here. Yeah. This we have seen. By removing these h's, this becomes a phase oracle. Correct? Now let's look at how things work. What will the first hammer do? It will take the state 0, create it into an equal superposition. We have seen this. So this will become correct. Now, so this is after 0 hammer to the power n. Now I apply oracle. my x was some x1, x2, xn, I get a phase of minus 1 to the power a1 x1 plus a2 x2 plus an xn. Question about this. What is the phase? Minus 1 to the fx times b. b is equal to 1. So the phase is minus 1 to the power fx. Notice it's minus 1 to the power, so I don't care about mod 2. Minus 1 to the power cube is same as minus 1 to the power 5, is same as minus 1 to the power 7. Right? So I can write it like this. Now,
There will also be another 1 by under root 2n coming down there, right?
why?
Like from there. Because
From the oracle.
wouldn't there be another under root 2n come down there?
From the oracle.
After the oracle, yes.
No. Oracle does not give a... For every x, it is converting just a phase. So there is no extra this. You can look at the oracle definition and you will see it. Right? I can put the required phases with the thing. Okay. So now this is the trick. You can interchange these. Is this troubling you? Huh? Yes? Okay. Let me write it summation x, right? So 0, 0. So I'll just do it for 2. Sorry. A0 times 0 Look at this summation, right? Do you see what is this? See, I am doing all possible multiplications between what will happen if I multiply this? A0, 0 with second term, third term, fourth term. Right? Sorry? Here. This is correct, right? If this is Still not clear. I shouldn't say A0, let's say. Or actually, yeah. What is this? Is this okay? This is fine. Now just choose B0 to be X0 to be 0. This is second bit to be 0. This is -1 to the A1 dot 0. This is -1 to the A0 dot 0. Right? And now, what is the header mode of this? What is the header mode of this? If AI is, then it will be 0. If AI is 1, it will be, so it is AI. Right? Sounds good.